Hey class, today we're going to be doing section 7.26b in AP Stats, which is our inference for regression. So today we're going to be looking at a linear regression hypothesis test. In the previous lesson, I went over the conditions for this type of regression, which is a whole lesson on its own. So if you haven't gone and looked at those, you'll want to do that first. Today I'm not going to talk about the conditions. I'm just going to talk about how to do the rest of the tests. So a linear regression t-test for beta enables you to test a hypothesis about the slope of the population regression line. So we're trying to figure out the slope of the population regression line and some hypothesis about that. Now, the most common hypotheses about the slope is that beta sub 1, our slope, is equal to 0, or that there's no association between the variables. So if we think about two variables in a linear regression, if they are positively correlated or negatively correlated, then there's some sort of either positive or negative association between the two variables. If the slope is 0, and it's all just kind of, there's no correlation, it doesn't all go positive or negative, and the slope is just 0, then you can say that there's no correlation between, or no association between the two variables. So that's usually what we're testing, beta sub 1 not equal to 0. So sometimes it'll ask you specifically if there's a positive association or a negative association. Then remember, these are just the most common. These aren't the only possibilities. So beta sub, or our alternate hypothesis, note it could be beta sub 1 greater than 0 or beta sub 1 less than 0. So we do see those sometimes, but only if the problem specifically asks you to test for a positive association or a negative association. A lot of the times they'll just ask for if there is an association or if an association exists. The test statistic, which is T equals b sub 1 minus beta sub 1. So that's our statistic minus our parameter over the standard error of our statistic. So, and degrees of freedom in this case is n minus 2. And again, in the previous video I talked about that standard error versus just S for standard deviation. They're a little different, so you'll want to go review that if you are curious. Example 1. A high school counselor was interested in finding out how well student point averages, or GPAs, predict ACT scores. A sample of the senior class data was reviewed to obtain GPA and ACT scores. The data is summarized below. So it didn't say it was a random sample here, but again, we're not really going to worry about the conditions. In this problem, it's going to say down here, to assume all conditions for inference are met. So we don't need to worry about the fact that it didn't say random sample there. All right, so you'll want to get your graphing calculators out. First thing we want to do is type all those in. So you're going to go to Stat and Edit, and then I've already typed these in. So you might want to pause the video and type those in now so you can play along. So the first thing we want to do is define our parameters, just like any of our other tests. So beta sub 1 is the slope of the population regression line that relates a student's GPA and their ACT score. Our null hypothesis, so is there evidence of an association between the two variables? So it's not asking if specifically if it's a positive or negative association, it's just asking if there's an association. So we have beta sub 1 is equal to 0, which would be no association, and beta sub 1 not equal to 0, which means an association would exist. Now, you might be asking yourself, because we did just do tests with chi-squared where we tested for an association. So you might be asking, why is this? How do I know if I use the chi-squared versus this? And the difference is in your data. With a chi-squared, we had categorical data where our values were just counts of how many people were in each category. Here we have numerical data. So that's going to be your main difference between whether or not to do a linear regression test or a chi-squared for homogeneity or association or independence test. All right, now, so we want to name it, of course. So linear regression t-test for beta. stated to assume conditions are met, and an alpha level, it said test an appropriate hypothesis at a 0.05. So this is stated as 0.05 level of significance. All right, so our t-score is going to be our slope of our sample line. So now I need to run this thing. So what we're going to do is go to stat, go over to tests, and all the way to the bottom. So I usually hit the up arrow, all the way to the bottom. Oops, sorry, up. You'll see lin-reg t-test. So linear regression t-test. I've got my X list in L1, my Y list in L2. I am testing for beta not equal to 0 for my alternate hypothesis. I'm going to run my regression equation in Y1, which is nice, and calculate. This is going to give me a lot of information. So it'll give me my t-score, which I will use. It also gives me my b value, which I need for my formula. So t equals b, which is 7.2934, minus our beta, which in our null hypothesis is assumed to be 0, divided by the standard error of our statistic. Now, the standard error of the statistic can be found, but you don't actually need to do the work to find it. So as long as you write it like this, you can usually get away with it on the AP Stats test. And if you're one of my students and you really want to know how to find that, you can let me know and I'll tell you. Sometimes it's pretty complicated unless you're given like the computer outputs for the problem, like the Minitab outputs. That's a little easier to work with. And I think I have an example. I do have an example in this lesson where I'll kind of show you where that is, but for this example, it would be a little too difficult to do. So we're just going to leave it like this. My t-score is 6.6937 or 38. So I'm going to just go 694. All right, and my degrees of freedom are 12. So notice that's 14. I had a sample size of 14 minus 2 is 12. And it's nice to show that calculation. Don't just put 12. Show the grader that you know how to find the degrees of freedom. It's n minus 2. All right, so my t-score, now remember this is a two-tailed test. And it's easy to forget, but when we're drawing our graph and we're finding our probability, we have to think about the alternate hypothesis. Is it an upper-tailed test, a lower-tailed test, or a two-tailed test? If it's not equal to, it's going to be a two-tailed test. So I have a t-value of 6.694 and a t-value of negative 6.694, and I'm going to be finding the probability on either side of those as my two-tailed test. So when I write my probability statement, I'm going to have t is less than or equal to negative 6. I'm just going to say 7, or t is greater than or equal to 6.7. And then I can write that probability down, which here I've got, 2.2 times 10 to the negative 5th. So that is 0.00005 or approximately 0. Now, I think, so to find that probability to show our work, we would usually do a TCDF function. So if I were to do that, I could go second, vars, go down to TCDF. And then my lower value, I can leave it at that and use my upper value of negative 6.694 with a degrees of freedom of 12. And that's going to give me, so each one of these is 0.000011, but so is this side, 0.000011. If I take that and I multiply it by 2, because I have 2 of those, I'll get that same p-value that we saw the test give us earlier. So you can show your work if you'd like to using your TCDF. Make sure to label your inputs on your paper. I don't have a whole lot of room, so I'm not going to write it down. You can sometimes get away with not writing it down as long as you have that probability statement stated, nice picture drawn. The rest of your work is pretty clear. Sometimes you can just kind of jump to the probability. The reason they let you jump to the probability, by the way, and why it's okay not to show the TCDF calculation is because technically we could find this value using the T-table and there would be no work to show. Now, with that said, using the T-table is kind of complicated, so I don't usually do it, but that's why they will accept your probability value without that work shown for the TCDF. It's not a bad idea to write it down though. All right, moving forward. So our conclusion, so our p-value is practically 0 since our p-value is less than or equal to alpha, which of course I have written down. Make sure you state your alpha. We reject H naught. So if I'm rejecting the null hypothesis, then I can say that there is sufficient evidence to support the claim that an association exists between GPA and ACT scores. So that's kind of a full, without the conditions, of course, a full hypothesis test for regression. Confidence interval for beta. So we have a confidence interval for beta is going to be our sample statistic plus or minus our T critical value with a degree of freedom of n minus 2 times our standard error of our statistic. And then just to FYI, I kind of mentioned this, SE of B can be found using the T-score given by linear regression t-test. And I'll kind of show you, I don't know, I'll see if we have some time here to show you that. I might be able to show you that. Okay, use the data from example 1 to estimate the slope of the population regression line that relates a student's GPA and ACT scores with 90% confidence. Assume all conditions are met. So again, we want to name it. We have a linear regression T interval at 90%. It's stated to assume all conditions are met, and we want to define our parameter, but it's the same as our example 1. So I'm not going to rewrite it, but I am going to state B sub 1 is defined in example 1 so that they know I at least thought about it. So now I'm going to use my calculator. I'm going to go to stat. I'm going to go over to tests, and I'm going to go down to lin reg T int. I still have my data in L1, L2. My confidence level is going to be 0.9 or 90%. I'm going to calculate that. Okay, now remember, we can't just write down our interval. We need to write down how to find that interval. So I have my B value, which is 7.2934 plus or minus our T critical value. So to find the T critical value for 90% confidence interval, think about it this way. We have 90% in between this value and this value in our confidence interval, which means our T critical value is going to be the T score with an area of 0.95. So I can use the NVT with a point, let's see. So I'm going to go to vars. I'm going to go to NVT. And my area is 0.95. My degrees of freedom were 12. And there is my T critical score. So 0.95 for my area. Degrees of freedom are 12. And I get T critical score is 1.7823. So 1.7823. So it's a little tricky because we have a 90% confidence interval, but it's a 95% area when we do this. The other way to do it would be to use your formula sheet. Go to your T-table. Look at the 90% column down here and go all the way up until you see 12 degrees of freedom. You get 1.782. So that's actually a little easier. If you want to use your calculator, you can, but that's actually a little easier. All right, and then we have times SE of B1. Now, again, we can find SE of B1 by running our T-score. So in example 1, we found our T-score. So going back to example 1, we had 6.694. So if I have, and I'm just going to kind of do it up here. So if T equals, so 6.694 equals my B sub 1, which was 7.2934 minus 0, divided by SE of B1, I can solve for SE of B1 using some algebra. So SE of B1 ends up being 7.2934 divided by 6.694, which is 1.0895. So I'm using my own calculator. I guess I could have used the one on the screen, sorry. So I could write 7.2934 plus or minus 1.7823 times 1.0895. So again, to get that, you saw my equation up here. Proportion rules state that I can switch these diagonals. So SE of B1 is the numerator 7.2934 divided by that t-score, 6.694. You don't have to find this, which is kind of nice. But if you do, it just gives the grader a little bit more to grade with. So one of those might bump you up to the next grade level sort of thing. I'm going to rerun my linear regression t interval so I can see what the interval is here. I have 5.3514 and 9.2353. I want to make sure somewhere that my degrees of freedom is still stated. I stated it over when I was finding my t-critical score, but let's just make sure it's really clear. All right, now we make our conclusion. I am 90% confident that the slope of the population regression line that relates GPA and ACT score is between 5.3514 and 9.2353. Now, what's really cool about this, in the first example we did, we stated that based on our hypothesis test, we could say that there was an association between the two variables. What the confidence interval just did not only is support that, but it actually shows us that not only is there an association, but there's a positive association. I love the confidence intervals because it gives you more information. So the connection to example 1, there's no 0 in our interval. If our interval went from negative values to positive values, then Z is in that interval, then beta could be 0. So that's what would tell us that we couldn't reject H naught. But if 0 is not in our interval, we can reject H naught. We can say that there is an association. And not only that, but this interval is all positive values, which means the slope of the population regression line has to be positive. So we have a positive association, which is really cool. So it supports rejecting H naught. So really, really neat. Sometimes problems will ask you to do both a hypothesis test and a confidence interval and connect the two. And I really like when they do that because I like seeing that connection. All right, computer regression analysis here. So just to kind of help you guys out with this, first of all, the computer analysis always assumes beta sub 1 is equal to 0 and beta sub 1 not equal to 0, which means when we see the p-value, it's always a two-tailed p-value. Sometimes they give you the computer analysis for a problem that's not two-tailed, and you'll have to split that p-value in half for your problem. So that gets a little tricky. This gives you your predicted Y variable. So that tells you that Y in this case is percent body fat. And then we have your degrees of freedom are here. This is your X variable. This is B sub 0, your y-intercept. This is B sub 1, your slope. This one is SE of B1. And then this is your t-score. And then this is your p-value here. But this, again, is two-tailed. So if your specific problem is one-tailed, you'll have to split that in half. All right, on the next page, I'm not going to do, let's see, I'm not going to do this page. Okay, so if you're my class, I want you to do this page. I have this highlighted because on the next page, we're going to come back and just talk about the difference between S and SE, which now that I realize earlier in this video, I told you I talked about it in the last video. I didn't. I talk about it now. Sorry about that. I prepped for both videos earlier and it got confused in my brain. All right, so difference between S and SE of B1 in a computer output. So the value of S in a computer output indicates the typical variation or standard deviation or standard error of the response variable for a given explanatory value. This is the same S as the linear regression t-test. So you can see on my score or on my screen still for my calculator, S equals 1.6269. This is not SE. This is just S. And this is not, so this is not SE of B1. SE of our coefficient is the typical deviation of the slopes. So not the deviation of the response variable for a given explanatory variable, but it's the typical deviation of the slopes of the sample regression lines generated by multiple samples. So example 4 says, explain the meaning of S in context from the computer output in example 3. So let's go back and let's just look at example 3 really quick. We have average monthly temperature in degrees Fahrenheit and electrical usage kilowatts per hour for our home. So the kilowatts per hour is our Y, average temp is our X. So S, which is here, is 201.3. So what that means is the typical variation in electrical usage in kilowatts hours or kilowatt hours. So that's our Y value, is 201.3 kilowatt hours for a specific average monthly temp in degrees Fahrenheit. So for a specific X value. The SE of B1 is down here, 4.980. And in context, that means a typical variation of sample slopes is 4.98, was it 980? If a large number of regression analyses were conducted. So if multiple samples were conducted, then the typical variation of the slopes would be 4.980. So be careful, try not to get those two things mixed up. And if you're in my class, go back and do example 3. And that is it for today's lesson.